to speed up so we could be able to cover. But like again, like I said last time, that this is where AI really begins, the graphical neural networks. That's what you hear about AI. So many magics that it's doing these days. It all begins from these foundations. So today we are going to be looking at how do we further strengthen our knowledge in area of graph neural networks. And we want to look at how we could be able to learn these graph structures, what they mean, and where the traditional neural networks fail. So one of the learning objectives today, basically, is that we want to explore at the end of this class how you were able to understand the concept of graph and graph structure. Also, for you to further understand what graph neural networks means and how they differ from the traditional neural networks. And also for you to be able to strengthen your understanding on what message passing means, and also the embedding space. And then we are also going to strengthen our knowledge on how these major architectures of the graph neural networks looks like, and then in the real world application. So it's quite going to be an exciting class where we're going to learn these interesting things. Now, graph is all around us. We are familiar with it, especially, in fact, right from elementary school. You have been introduced to this concept of graph. I think right from my primary school level, I already knew what was a pie chart, a histogram, and all that. Not in the complex way that I was introduced in the secondary level, but then I was already familiar with what this graph means, and all that. So, but by definition, we said graph is this non-Euclidean data structure that represents relationships between entities. Now, when we talk about entities in this case, we have to know that we are talking about the entities can be human being, it can be objects, it can be anything that we want to represent, to be able to create some sort of relationship with another entity. So the component of graphs are nodes or vertices, which we call them entity or object of the graph. Though there is an interesting part we call edges or the links, which connects the relationships between these entities. So the nodes on its own doesn't tell us anything if it doesn't have connections that are linking them to the various other nodes. Now, there are different types of graphs. It could be direct or undirected graphs. It could also be homogeneous or heterogeneous. It could also be static or dynamic. Now, when we talk about the graph, most of the time, the representation we are focusing on is the adjacent matrix, which focused on the list, the edge list, or the future matrix. We will see that briefly. Now, when you look at this figure here, you will see that what we call the nodes are the round figure that has the number 0, 1, 2, 3, and 4. Now, the edges are the ones that connect them. We know normally from the ordinal way of viewing numbers 0, 1, 2, 3, because they are ordered, you will know that once you are moving from 0, you move to 1. From 1, you move to 2. From 2, you move to 3. Now, we can't say if the magnitude of the relationships are the same, but we know that the hierarchy is usually 0, 1, 2, 3, or we could count by reverse 4, 3, 2, 1, 0. So you could either go ascending or descending. Now, that sort of relationship where you go one way or you come back the other way, you could say is direct or undirected, you know. So when we talk about that direct, it's usually it doesn't have an arrow pointing to where the node is connecting to. But usually it's just this relationship between without any form of, you don't see any arrows coming in or going out. So we say that's an undirected graph. But the one that usually we see an arrow pointing to a direction that the nodes go into or come out from, we said it is a direct graph. Now, we can see graphs as images. Yes, we can view images as graphs, not just, pixels. Remember I told you guys when we were looking at GNNs, that they work with images. And usually the way it works with images, it see them as pixels of grids. And then it could zoom into each of these pixels and carry out some sort of matrix manipulations at each layer of the convolutional neural network. And then at the end of the day, it tells us if it's a cat or a dog. So in like manner too, we can see graphs as images, not just pixel. But in the case of pixels, each of the pixels that we see, we consider them as node connected, up to 8 neighborhood, or depend on the scaling you are using, 2 by 2, 5 by 5, and so on and so forth. So the node futures in this case are RGB, that's red, green, and blue. But if you know the RGB, it is a 3-vector format. Okay. Now the 3-vector format itself, tells us about this matrix representation where we are focusing on the adjacent matrix, to see the connectivity in the pixels. Now, in same images, the data set can be represented as grid or graph structures. And then we can also represent it as matrix. Now, this is what we mean. If we have, I don't know, is this picture quite clear? Can you really see it very well?
Yeah, very clear.
Okay, so if we looked at this image, you could actually see that these pixels, you zoomed, each of them, they are represented as this grid, like, or sort of, we can say heat map, in the first image here. However, when we put them on the number line, we consider them based on the adjacent matrix. And each of these adjacent matrix is still like, again, you can connect them in form of the node and edges. So if you have 1, 1, 1, 2, 2, 2, and all that, you can represent them and say this is where the node is, and this is what is leaving the node to each edge. So the same way that we looked at it in the traditional neural networks, where we zoom into each part of the pixels, the grid, to look at what is happening to that pixel, the same way we could represent them in form of graph. In similar manner, we could also consider text as graphs, where each of the texts can be digitized by assigning indices to characters, words, or tokens. Now, remember I told you guys last time that when you have a sentence, it breaks it down into this lemma of characters, what we call token. Now, those token and be represented, as a graph where each token can be considered as a node, forming a sort of a direct graph, and each of the edges will be that connection between each node or sequence to the next one. And this is to help us to be able to capture that structure or ordering in the language, of the graph. Now, usually when we are dealing with natural language processing, it is very useful. We can use this kind of graphical neural networks to help us to recognize which of the word the token has more weight than the other one. For example, this word graphs are all around us. Now, the ones with more weight will be all around. So that kind of way of assigning this weight, we could represent it in form of a heat map where, remember we said the adjacent. So usually that adjacent is what we'll be looking at and telling us what kind of relationship is happening between the node and the entities, and also the edges, which of them are cross-talking to each other. Because usually the node itself, like we said, is in isolation until we begin to study the neighborhood of that node to see what sort of connections is happening around them. So in the wild, we could see that naturally data are very irregular and heterogeneous. We do not have this one beautiful way of saying data would always be structured. Our data will come in different formats, whether unstructured or structured, or semi-structured and so on. Most of the time, the data are collected in different forms. Like I told you last time about satellite images. When you look at the satellite images that is coming to us, or even waves, that we're collecting, you will see these data are not friendly. You have to make sure you put them in the right formats in order for you to read the right signals from these data. So the node have variable numbers of neighbors. This cannot be easily represented as grid or sequences. So the best way we could picture that is to use graphs. Now, examples is the molecules in chemistry. Now, when you looked at the atom, in chemistry, you would see that the molecular structure, I don't know if you still remember your chemistry, but I remember doing carbon or something. We call it organic chemistry. In the organic chemistry, especially when you are doing hydrocarbons, you would see the relationship between the carbon, the hydrogen, and the oxygen. And then I think C2H4 should be either hectane or something. Then you move to another one, then you get to that level where you even begin to look at things like glucose. You see the structure of glucose. You begin to move into complex hydrocarbons, and what is really happening there. So those kind of data, they are very complex representation. But we can look at it in a graphical form where the molecules could be atoms, which we could say they are nodes. Then the kind of bonding that is happening between them, is it a covalent bond? Is it van der Waals force or some sort of electrostatic bonding, or any kind of bonding happening? That kind of bonding becomes the edge. So the molecules are the mix or the addition of the atoms and the edges that binds them. Because remember, I just gave you an example of the carbon, hydrogen, and oxygen. So this kind of molecules usually are paired or come together as a result of the sort of bonding that happens between them. Either it's a covalent bond or some sort of electro static bonding. Now, the covalent bonds form the edges in the atom in stable configuration. Now, if you do balancing of chemical equation in chemistry, you will know that you have to have some certain molecular weight or something for you to say that equation is balanced. Once it doesn't agree, that particular molecule or something is not stable. you know. There is a good example. I'm trying to figure out to think about. I think benzene or something. It's one C6H6 or H2. One of them. I can't remember my chemistry that well again, but I know that you have to have this way of making sure that the left side of the equation is balanced with the right side. Else, you have a problem. So the edge types in this case could be single, double, or triple bond. And if you do chemistry very well, or you talk to chemists, you will see those representation. Um, if I can, remember very well, you will see something like C3, let's say H, um, maybe six, and then you see these two arrows somehow, and then you will see something like maybe C something two, maybe O 7 or something. I know I don't think 7 is anyway. You will see something like this if you remember your chemistry. And maybe this on this one here, you will see that it's usually one arrow pointing to another one, maybe a hydrogen or something. And then you could also get to see probably a triple bond or something pointing to another thing, maybe a nitrogen or something. I can't, like I said, I can't remember my chemistry, but I knew I've seen this kind of uh bonding structures. We have single, triple, and double bonds, stuff like that. So the graph structure could help us to see these molecular structures in a compact or flexible form. So you could see that in this case, this particular structure here, we could look at the adjacent to see how it's being represented. And from there, we could take a lifting of it to put it in form of this graph. So this is a representation of a caffeine molecule where the adjacent matrix of the bond in the molecule, that's the right graph, is a representation of the molecule. So, we could see it in this different graphical network. Now, in similar version, we also have the social networks. We can represent the social networks as graphs. Now, if you're familiar with the social networks like Facebook, TikTok, Instagram, even LinkedIn, all the social networks that we have, cookie dating sites and all that, you will know that most of the time the suggestions that you get for friendship, collaboration, or communication is based on probably your profile and also your location. It could be even on your gender, it could be on your age, it could be several things. Then if it recommends, for example, if I open a Facebook and I put my location, United States or United Kingdom, I'm going to have this strong recommendation of people from that locality. So if I now go down to put my location at Houston, Texas, or London, I'm going to see the friends or people that will be suggested to me or activities will likely be within London area. The same thing if I opened in Italy and I put my location at Florence or Rome, I'm going to see the people suggested to me will be from that location. But then you will now see that by the time you linked up with your friends, maybe friends from primary school, secondary school, or tertiary or college, you will begin to see their other friends of their friends pops up. So if Monday is my friend or John is my friend, I'm going to see people that are friends to John coming up for me or suggested as friends, stuff like that. So these in, uh, social network platforms like Facebook and all that, they use these social networks to make this sort of recommendation. So, they use to study patterns in human and organizational behavior, and each individual in this case is going to be a node. So that individual could be male, you could look out for several attributes, maybe male, he's 24 years, he likes football or something, right? He likes football, you know, or you could have several characters. So based on that information that person has given, they can now begin to establish edges or relationship. So the edges now represent the relationship, that friendship that you begin to suggest, some of the activities or communities, that are around him. You begin to see that kind of suggestions coming up. So this uh, kind of social network could be able to model complex, large-scale social structures and interaction. It's very, very useful when we are looking at influence analysis, community detection, and recommendation system. This is very, very useful for us to be able to carry out such kind of approach. Now, this image here, it's graphically in the matrix form or heat map form, like I said, the adjacent matrix, you could represent it as this. And also you could further lift it up and represent it in a graph form as this, where we said the left image seen from the play Othello, centered adjacent matrix. Like I said, we could leave, and then we could look at the graph representation of the interactions that are happening between them. Now, there are different types of graphs or graph structures, because if you don't understand the problem, you can't be able to apply it. So you need to understand the problem and how you could be able to use this graph to solve your problem. I don't know if you guys are with me. Are we together? So we have been talking about the introduction to class and all that. Great, great, great. Okay, so the first problem that you will likely encounter is trying to use the graph for trying to use the graph neural networks for graph level prediction. So when we talk about graph level prediction, we are talking about predicting the entire property of the graph. Now, you have to understand that it means that if I have this large social network graph, or even a fraud detection graph, or whatever problem I have, I feed everything to the AI and tell it I want it to observe these patterns and make predictions for me. So it means that could come as a classification problem, or a regression problem, or even a clustering sort of problem. So just like the way, remember we talked about earlier on when I was teaching you about machine learning, I told you that the machine learning could be semi-structured, it could be unsupervised, supervised, or semi-supervised learning approaches. But we have been focusing on the two unsupervised, supervised, when we talk. So in similar form, we can also talk about it even in the graph neural networks. we still have the unsupervised, supervised, and all that. But remember, we said the supervised it's looked in two ways: the classification and the regression problem. So a good example is this picture here, where you have this graph here, looking like this, and you have to make a prediction on the entire graph. So when you feed this graph as an input to the GNNs, you are likely going to have it, split them into this form and say this one and this one belong to the same class or category, while this one and this one belong to the same category. Now, you could see one of the things it will be looking at is the number of rings, the number of rings. You can see this one has two rings, one, two. There are these two close rings inside them, and there is also that ring here. So the network will automatically know that these two are similar. But when you also look at this one, you will see that it doesn't have a close ring. Just like here too, there is
I'm
no
not seeing your
close ring.
I'm not seeing your pointer. I'm not seeing
Okay,
your pointer. I'm not seeing what you're pointing at. Okay.
you can you see this? Can you see this? The red.
Yes, I can see. I can see.
Good. Now you could see this one here has one ring, and this one here has one ring. So the network would automatically uh classify them to have similar structure, so they belong to the same category. When it comes to this one here, the network will look at the ring, which is this ring here and this ring here, and automatically classify them to be in the same category. Okay, so that sort of similarity checks that the network does on the entire graph is what we call the graph level prediction problem. Okay, now there are also situations where we are interested at the node level prediction. So in this case, we are not interested in predicting the entire graph like we saw in the previous slide. Rather, we are focusing on predicting a label or a value for each node. Now, example is if we want to classify users in a social network as bots or humans, because these days, especially with the rise of agentic AI, we are beginning to see that so many organizations want to save a lot of resources by employing AI to do most of the, heavy lifting work for them. And you don't even know when, sometimes, I don't know if you have ever logged into a site and then the next thing you see this chatbot pops up and say, hello, how can we help you? And then once you engage that chatbot, it begins to reply. You may think and say, oh, you're chatting with a human, but that's a chatbot. It's not a human, stuff like that. So there are so many social media accounts that you see these days that they are chatbots. They are not humans in the end. And AI these days can be configured to even be chatting with people. There was this story I read last time of this guy that started making a lot of money when he used ChatGPT sort of model to develop a kind of a girlfriend, a ChatGPT sort of girlfriend. So when he did that, create a very nice picture from some of these stable diffusion models and all that. Create a nice profile and put it online. So some men that were lonely or they are searching for partners or something, they started engaging and chatting, thinking they were chatting with the lady or at the other end without knowing it was just a chatbot. And many of them were subscribing and all that and all that. So there is a situation where you want to analyze to know if this is a chatbot or it's a human. So that's where the node classification or prediction problem comes into play. So when you look at this network here, for example, you're beginning to predict. So when you feed the whole unlabeled node into the network, you're going to be predicting, for example, where these particular individuals could be and where these other individuals could be. So you're basically going to be looking at the relationship that exists based on the neighborhood. So you look at all the neighborhood around that particular node. That tells you the strength of the interactions that are happening around it, stuff like that. Then there is also another interesting problem, which we are looking at the edge level prediction. So in the edge level prediction, we are focusing on the relationship. So we want to predict the relationship between the nodes. So if we want to predict the relationship between the nodes, we want to look at the links if they actually exist between them. So example is we predict if a link exists between two users. So we can use also the task here is going to be either classification or also a regression problem. Now, this example of Karat, was presented to us, or was Karat a student or something. So look at the picture. When you looked at the picture, you could actually see if this guy is it fighting with this person here. So if this is Johnny, this is Daniel, and this is the referee. The referee, what he's doing basically, he's watching, and these guys are fighting. So when this Daniel lifts up his leg, he's either going to attack Johnny, or and then the referee's duty is to watch both Daniel and Johnny, and then there are the audience that are actually standing on or watching, from the outside. So you can easily represent it as a graph and create that sort of relationship where we have fighting, watching, and standing on, stuff like that. So but nothing comes without a challenge, of course. And also the graph data has its own challenges. So one of the biggest challenge of the graph neural networks is that uh, it struggles. It struggles a lot with unlike the normal traditional neural networks. The graph neural networks has to deal with graph data, not pictures and all that. Okay, so if the standard neural networks, that's the CNN, RNN, are designed for structured data, like a grid of sequence and all that. Now, I'll make emphasis on that. When you looked at if you follow the last class on convolutional neural networks and recurrent neural networks, you would see where we said the convolutional neural networks handles image problems and object detections. And then we said the recurrent neural network, on the other hand, has its strengths in text sort of data or time series, or sequence sort of data. Then when you looked at all these data, both the image and the text, they are actually structured data. Now, when we talk about structure in this case, we're looking at the fact that this data had some sort of ordering. In the case of the images, we said the image can be split into multiple grids of pixels. So that multiple grid of pixels, at each layer that you feed the the image to the convolutional neural network, it will create this sort of 0, 0, 1s of matrix. And then it looks at which of the matrix layers and do its addition and multiplication or subtraction, and then moved into the next layer and does the same sort of manipulations, moved into another hidden layer, as so on and so until it gets to the output layer. That's a structured data. When you look at sequence time series kind of data, they are also ordered in such a way that the memory cell can easily hold this information and be able to make all sort of analysis. And then at the end of the day, it could get to the output layer and then the decision will be made. But in the case of the graph, it is a very complex data such that these neural networks can't be able to handle them. One of the reasons is because the graphs can be dynamic, irregularly structured, and have varying numbers of neighborhood. This neighborhood could be up to millions, will be up to thousands. So by the time you are trying to represent them in the normal way, there is high tendency you could suffer from cost of dimensionality, sparsity, and so many issues could come up for you because of the complex nature of these approaches. So the traditional method loses this crucial information, which are represented in form of nodes and edges or relationships, which is what you are interested in looking out for. So you see that the traditional methods actually fail. So we can't be able to use them for graphs because the graphs are very